Welcome to AI Journal Club, the digital pathology podcast segment where we take a closer look at the research shaping AI in pathology. This episode is one of our AI-powered summaries series, AI-generated deep dive into a paper worth your attention. It's curated from our weekly DigiPath Digest live stream that I run every Friday morning. I'm Dr. Alex Żuraw, and this is your shortcut to stay current. Let's dive into it.
Hello and welcome back, Trailblazers. You are listening to the Digital Pathology Podcast, the show where we get past the surface and look at the code, the cells, and the systems that are changing how we practice medicine.
That's right. And if you're tuning in, you probably know the days of the lone microscope are, well, they're numbered.
It's more than a tech upgrade, right? We're talking about a complete paradigm shift.
It's a total shift, and it's already here, just not evenly distributed yet.
Yeah.
Today we're not talking about, abstract futurism or hype. We are getting our hands dirty with the actual blueprints.
The nuts and bolts.
Exactly. The hard requirements for building a digital lab that is actually safe for patients.
And for that, we're breaking down a huge piece of work. It's from Diagnostic Pathology, published in 2026 by Szylberg and colleagues. The title is Guidelines for the Adoption of Digital Pathology in Clinical Pathology Units, recommended by the Polish Society of Pathologists.
Now, hold on. Before anyone tunes out because they don't practice in Poland, don't. This document is fascinating.
Why is that?
Because it's one of the most comprehensive soup-to-nuts frameworks I've seen. It really bridges the gap between high-level medical guidelines and detailed IT specifications.
It's basically a how-to manual for turning your glass slide operation into a data center. So today we're going to cover the hardware specs you really need, the frankly terrifying amount of data storage, and the validation process.
Right. Our mission today is to give you the specific standards, the numbers, the microns, the pixels, the things that separate a shiny tech demo from a clinically safe diagnostic machine.
Because if you get this wrong,
you're not just wasting money, you're risking a misdiagnosis.
High stakes. Let's start at the very beginning. I think the biggest misconception about digital pathology, or DP, is that it's just, taking a picture of a slide.
Oh, if only it were that simple. Szylberg and the team make this point right at the start, and it's the foundation for everything. Digital pathology doesn't start at the scanner.
It starts at the microtome, at the knife.
Exactly. The garbage in, garbage out rule.
Explain that.
Okay. Think about a traditional microscope. You have a glass slide. If the section is a little thick or maybe it's folded, what do?
You use the fine focus knob. You adjust it.
You twist the knob. You scan up and down through the z-axis. Your brain and your hand compensate for those little imperfections in real time.
But a scanner can't do that. It takes one picture, more or less.
Pretty much. For high-throughput diagnosis, it's usually a single focal plane. Once that whole slide image, the WSI, is created, the focus is locked in. You can't refocus a blurry image on a screen.
So the physical slide has to be basically perfect.
It has to be perfect. The guidelines are incredibly strict here. They say paraffin blocks must be sectioned at exactly 3 micrometers.
3 microns? Wow. I mean, standard practice can sometimes drift to 4 or even 5, can't it?
It absolutely can. And with a glass scope, you might get away with it because you have that depth control.
Yeah.
But with a scanner, no chance. The autofocus gets confused and you get these blurry patches that you just can't diagnose.
And it's not just the cut, it's the mounting too.
Oh yeah. The mounting medium has to be perfectly even. No air bubbles. An air bubble acts like a tiny lens. It refracts the light and the scanner's autofocus hits it and throws the whole field out of focus.
So you get a beautiful high-resolution image of an air bubble.
A beautiful image of garbage. And you can't diagnose garbage. This forces a quality control step that maybe wasn't as rigid before.
But once you have that perfect image, that's when you unlock the benefits.
That's it. You break the physical chain of custody. No more waiting for trays of glass to be walked down the hall.
Or shipped across the country.
Precisely. It becomes a software problem, not a logistics problem. Urgent cases, like an intraoperative consult, can just jump to the top of a digital work list.
Okay, so our 3-micron slice is perfect. We move to the engine room, the scanners. This section of the paper felt like reading specs for high-end photography gear.
Well, it is high-end gear. The guidelines say the scanner resolution must be equivalent to a 40x objective lens. But 40x is a bit vague, so they give us the magic number.
Which is?
Less than or equal to 0.26 micrometers per pixel.
0.26. Why so specific? Why not 0.3?
It's about resolving power. It's about cell biology. You need to see the chromatin pattern inside a nucleus. Is it smooth or is it coarse and irregular?
And that can be the difference between benign and malignant.
It's often the key difference. If your pixel's too big, say 0.5 micrometers, you just see a blue smudge.
That's right.
You lose the texture. You need that 0.26 to make the call safely.
So that's the threshold for diagnostic safety. Now, there was another detail about scanners I found fascinating. The scanning strategy, how it decides what to scan.
I'm so glad you brought that up. This could be a silent killer in DP.
Because I just assumed it scanned the whole piece of glass.
Well, to save time and storage, a lot of scanners do a quick low-res preview scan. They find the tissue, and then they only scan that area in high resolution.
What if the tissue is really faint?
Exactly. What if it's a tiny cluster of cells? The machine might think it's just dust or scratch. It skips it. And if the machine skips it, the pathologist never ever sees it.
So what's the recommendation?
The Polish guidelines say you need protocols that map the entire slide area, except for the label. It's slower, yes, but it guarantees that if something's on the glass, it gets on the screen.
You can't trade safety for speed.
It's non-negotiable. And speaking of speed, these machines are workhorses. The paper mentions a workload of 200 to 300 slides per day per device.
That is a heavy load.
It is. So you need consistency. They talk a lot about color fidelity. Scanner A in one lab has to produce the exact same shade of pink as Scanner B in another.
Because color is a huge part of pattern recognition for a pathologist.
Huge. If the eosin looks a bit off, it creates a cognitive friction. You spend mental energy just adjusting to the color instead of diagnosing the disease.
Which is the perfect segue. The image is captured, it's high res, it's color accurate. Now we have to display it. Welcome to the pathologist's cockpit.
A cockpit. I like that. It is a command center.
This feels like where a hospital might try to save a few bucks. Hey, you've got a nice Dell monitor, just use that.
And the guidelines just scream, please do not do that. This is probably one of the strongest sections. Using a standard office monitor is a diagnostic risk.
Okay, so walk us through the specs. What do you actually need?
It starts with resolution. Minimum 2560 by 1440, but they strongly prefer 4K. That's 3860 by 2060 pixels.
On a pretty big screen, right? Like 27 to 32 inches?
Yes, size matters here. 27 to 32 inches at 4K resolution is the sweet spot. It mimics the field of view of a traditional microscope eyepiece. It just feels right.
What about things like brightness and contrast?
So brightness needs to be at least 300 candelas per square meter. But contrast is even more critical. They want a ratio of at least 1,000 to 1.
Why is contrast so important?
Because pathology is all about subtlety. You're looking for a slightly darker nucleus, a faint wisp of something. If your blacks are just dark gray, those subtle features literally disappear. You can't see the disease.
And you can't just buy it and forget it, right? There's a maintenance part.
Monitors die a slow death. The colors drift. The guidelines mandate regular hardware calibration. You actually use a physical probe that hangs over the screen to adjust the color profile back to true.
You are calibrating your primary diagnostic instrument.
That's exactly what it is.
Okay, we have the perfect slide, the massive scanner, the 4K cockpit. But now we hit the invisible monster of digital pathology, the data mountain.
This is the part that gives IT departments nightmares.
The paper states a single 40x slide is about 1 gigabyte.
1 gig per slide.
So a lab doing 300 slides a day, that's 300 gigabytes of new data every single day.
It's an avalanche.
Yeah.
To keep just a 6-month active archive, meaning slides you can pull up instantly, you're looking at around 50 terabytes of storage.
And that has to be redundant storage?
Absolutely. They recommend NAS network attached storage with RAID redundancy. That means the data is spread across multiple drives. If one drive dies, you don't lose the patient's data. That is medically unacceptable.
Here's the fascinating legal twist, though. Even with all this digital storage, we still have to keep the glass, don't we?
Yes. For now, glass is still king. In Poland, and it's similar in the US and UK, you have to keep histology slides for 20 years.
So the basement is still going to be full of boxes.
It is. The digital archive is for workflow. The glass is for the law. But there is a really cool exception in the guidelines that points to the future.
The digital original idea.
Precisely. If a glass slide breaks or fades or gets lost, in those specific cases, the digital image becomes the primary medical record. And then it has to be kept for the full 20 years.
It's like a backup of physical reality. Now, what about the cloud?
The guidelines are cautious, but open to it. But the rules are strict. GDPR compliance is non-negotiable. For them, that means servers have to be in the EU.
And security is paramount?
Of course. TLS encryption, two-factor authentication. But the real bottleneck is speed. They recommend a minimum upload of 100 megabits per second.
Which feels maybe a bit slow.
The minimum. But imagine you're working from home, and that 1 gigabyte file takes 2 minutes to buffer every time you zoom. You can't work like that.
Yeah.
It's not just annoying, it's a clinical risk.
How is it a risk?
Because latency causes shortcuts. If it takes too long to zoom in, a pathologist might, subconsciously decide to diagnose at low power. They might skip a corner of the slide. Speed is safety.
That's a great point. So we've built the system, but we haven't talked about the most important part yet, the human. You can't just drop a pathologist in front of this and say, go.
No. And this is the part of the guidelines I respect the most, the validation protocol. It's like learning to fly a new airplane. You need flight hours.
They follow the RC-PATH model from the UK. It's a formal study.
Very rigorous. It
Right.
starts with familiarization, just learning the buttons. Then you move to the retrospective phase.
Looking at old cases.
Yes. At least 20 archived cases, and not easy ones. You want the hard stuff. You diagnose them on screen, then check your answer against the original report. It's a self-test.
But the real test is the prospective phase.
That's the one, the dual assessment. For 1 to 3 months, you diagnose live cases, but you have to do it digital first.
What does that mean, digital first?
You have to look at the screen, make your diagnosis, and write it down. Only then are you allowed to pick up the glass slide to verify.
Ah, I see. So you can't be biased by looking at the glass first.
Exactly. You have to prove you can reach the right conclusion with the screen alone without the crutch of the microscope.
And if you find a discrepancy?
You document it.
Yeah.
You analyze why it happened. Was it the image quality? Did you miss something? You don't get signed off until you resolve those issues.
And once you pass?
You get a certificate, you're validated. But here's the kicker. If you switch specialties, say from GI to derm path, you have to revalidate.
Really?
Absolutely. Diagnosing a polyp is visually different from diagnosing a melanoma. The guidelines respect that. Your validation is for a specific context.
That's incredibly thorough. Okay, so once you've climbed this mountain, what's the payoff? The guidelines look to the frontier, AI and telepathology.
Right. And AI is framed as a tool for standardization, not replacement.
They mention biomarkers specifically, Ki67, HER2.
Yes. Things where a pathologist has to count hundreds of cells, what percentage are brown. Humans are notoriously bad at that. AI doesn't get tired. It counts every cell the same way every time.
It removes the subjectivity.
Drastically. So lets the pathologist do the thinking while the AI does the tedious counting.
And then there's intraoperative telepathology. The patient is on the table.
The surgeon is waiting. They need to know, did I get all the cancer out? Time is critical.
The 5-minute rule.
That's it. The digital slide has to be ready for viewing within 5 minutes of the glass being made. You can't have a slow system here.
But what if the Wi-Fi goes down mid-surgery?
That's why you must have a backup plan. A physical scope on a card, a separate phone line, something. You can't tell a surgeon, hang on, the router's rebooting.
So let's recap this whole journey. We start with a 3-micron slice.
Run through a 0.26 micron per pixel scanner.
Stored on a 50-terabyte server.
Viewed on a calibrated 4K cockpit.
And interpreted by a pathologist who spent 3 months learning to fly the ship.
It's a massive undertaking. But it creates something new. Not just an archive, but what they call active biobanks.
Explain that.
A glass slide in a warehouse is dead storage. But a digital slide in a database is data. It can be mined. Reanalyzed by new AI algorithms years from now, it unlocks the hidden value in the tissue.
Which brings us to a final thought for our trailblazers. We treat the glass slide as the legal gold standard. But glass breaks. Stains fade.
After 20 years, it might be useless. But the data, if it's backed up properly, is immutable. It's a perfect snapshot in time.
So are we heading to a future where that digital original isn't just a backup, but is actually the truer medical record?
I think that's exactly where this is going. The pixels might just outlast the atoms.
Something to think about. We want to thank you, Trailblazers, for joining us.
Stay rigorous, keep those monitors calibrated, and we'll see you next time.
That's it for this AI Journal Club episode. If you want more like this, make sure you're subscribed to the Digital Pathology podcast and come join us for the DigiPath Digest, our weekly live session. During these live streams, you can vote which paper becomes an AI deep dive. And if you're serious about digital pathology, grab my free book at digitalpathologyplace.com. This is the best place to start your digital pathology journey. Thank you so much for listening, and I'll talk to you in the next episode.